Okay, so if I had to, don't draw yet, if I had to give you two different shaped triangles. And we discussed the fact that we have shape and we have size. And then I also heard the length of sides, so how long a side is, and I heard the size of angles. So which one of these two, length of sides and angles, would cause the triangle's shape to change? Okay, fine. Let's do that. So I'm taking that triangle. Let's call it 2, 3, and 4, the lengths. 4, 6, and 8. I changed the length of sides, didn't I? I doubled. But did the shape of the triangle change? Those two triangles still have the same shape. So if the size of the sides doesn't affect the actual shape of the triangle, that means that the angles have to. So this angle is exactly the same as that angle. And this angle is exactly the same as that angle. And my third angle, therefore, three angles of a triangle, or interior angles of a triangle, has to be the same as that angle. So the angles stayed exactly the same. They're still similar, they still have the same shape, but the lengths doubled. Now let's compare these two triangles. Do those two triangles have the same exact same angles? No, I mean this one's probably got a 90 degree there, this one's very small, that one's a little bit bigger. So my angle influences the shape, and the length of sides influences the size of my triangle. Now the reason why we're bringing this up is when I start proving that two triangles are similar, I want to prove that they are exactly the same shape, but that the size can be different. So in our books we're going to write the following. I'll zoom in for the notes. Let me just put this off, I think it's causing a problem. Okay, we are 8WY. It is Monday. And we are group 2. Today is the 28th of September. Okay, our new topic is similarity. And specifically, we are going to be comparing triangles to each other. Now, just like parallel lines, similarity has a unique symbol. So when you see it, you need to know that I'm referring to similarity. Now, parallel lines were two lines like that. Similarity has a third line. So whenever you see three vertical lines, I am referring to similarity. So that is the unique symbol for similarity. What do we do in similarity? We are comparing two or more triangles to each other. So for a triangle to be similar, it must look the same. It must have the same shape.
Could it be any other shape?
Yes, it could be, but it becomes more complicated to prove. So we just do triangles because then it's only three things we have to prove. a quadrilateral, then it's 4 things that we have to prove that they are similar. So we want the same shape, but they can be a different size. So in order for them to be the same shape, we need to have corresponding angles that are equal in size. For it to be a different size, it means that they have different side lengths. But there's a very important but. So even though the side lengths are different, the proportion is the same. And we're going to look at what proportion means in a moment. So when I talk about sides that are in proportion, remember we spoke about the fact that these 2 triangles that we had, this one and that one, we doubled every side. That is what I'm talking about proportion, that the one side length increases with the same amount as the other side lengths. Okay? So sides are in proportion is when every side increases with the same amount. So I'm just going to make a note here. And when I say same amounts, we actually have a mathematical term. It's called a factor. So each side increases or decreases with the same factor. Okay, so let's just practice that for a moment so we understand exactly what we mean by proportion. Because proportion is one of the biggest ideas that we need to get our heads around when it comes to similarity. So if I have a line, and I say the length of that line is 2, and I want you to increase it by a factor of 3. Increase by factor of 3. That means I want to make my line 3 times bigger. So i.e. make 3 times bigger. So what is the length of my new line going to be? 6. 2 times 3 is 6. Now visually it doesn't really look like it, but the numbers tell me that it has increased by a factor of 3. So what factor did I increase 3 by to get 218? 6. I increased by a factor of 6, or 3 times 6 gives me 18. So I can go forwards, backwards, reverse. Let's do one more. If I had something, I increased it by a factor of 4, but the answer is 4, what did I have to start off with, Laszlo? I had to start off with 1. 1 times 4 gives me 4. Or backwards, 4 divided by 4 gives me 1. So forwards we would times, backwards we would divide. So that is what I mean by proportion. That there was a factor that I multiplied to get the new line. So after everyone's written down, let's see how this works in triangles. Anyone still writing from the board? Okay, let's look at some triangles. So just a random triangle, and I'm going to tell you that it's 2, 4, and 10. Does that make sense visually? No, it doesn't. It's not to scale. But it is numbers that we have to work with. So if I want to increase it by a factor of 10, two times 10, 20. 4 times 10, 10 times 10. But now where am I going to put that 20, 40, and 100? Can I put it anywhere? Why not? Tariq says we can. Laszlo? So on the left-hand side, the right-hand side, and the bottom. Okay? What if I did this? Left-hand side, bottom, right-hand side. I like that word, yes. Tariq, yes, I'm listening, Lazo. Rotate, not quite. The proper word is mirror or reflect. But yes, what you are finding is corresponding sides. The sides that match in each of my triangle. So that's exactly what we have to make sure, is that my corresponding side is what has increased. Corresponding side, corresponding side. So try this one for me. Decrease by a factor of 2. Are those numbers going to get smaller or bigger? Smaller. So I want those corresponding sides to get smaller by a factor of 2. Okay, so this line on the right-hand side, what value do I have there now? The value at the bottom? And the skew line? So we said 8 divided by 4 with the corresponding side. 6 divided by 2 with the corresponding side. And 22 divided by 2 with the corresponding side. So that's a very important note. So very NB, very, very, very important. We must match the corresponding sides. Corresponding just means we are comparing two things. So I'm going to make it slightly more difficult, and then we're going to get back to our notes. Okay, as your last one, I want you to find the two missing sides. You said it was just aid and absence. I'll quickly do that absentee check. So we know that we are multiplying by 8 if we go from this side to that side. We also need to match the sides. So 12 times 8 is equal to, pardon? 96. So this side here, I'm going to do with a squiggle, is matching with this 96 there. Okay? The skew line opposite my 90 degree must also be the skew line opposite my 90 degree. Thank you. Okay, squiggle line 12, 96. My skew line, my hypotenuse across from the 90 must be my hypotenuse across from the 90. So what did I times by 8 to give me 72, Laszlo? 9. So I'm going to do it in green. Or I said 72 divided by 8 gives me 9. So this was the corresponding side to that. Which means my third missing side, what am I going to do? Someone other than Laszlo. Tyreek?
4 times 8.
Gives me
32.
32. Fantastic. And now if you got that, the word is about to come will be slightly easier.
What's on the lesson end?
10 past. Okay. So the assumption that we made here at grade 8 is that these triangles were similar. And we assumed that because they had the same shape, right? We looked at them and we decided, okay, they're the same shape, therefore the factor would work. But in maths, we can never assume anything. We need to be able to prove that they are similar. So if we need to prove that they are similar, we need to prove that they are the same shape. Shapes, or the shape is influenced by the angles, therefore we have to prove the angles before we could actually say any of this stuff. So let's see how we would prove it before we calculate. So there's a specific format that we need to prove. Okay, so in maths, we cannot assume that the triangles are similar. We need to prove it. Okay, I don't know why it's too much. So in maths, we cannot assume that the triangles are similar. We need to prove it. Now, similar means same shape. Same shape means same angles. And again, I'm using this word corresponding because I'm matching triangle angles from different triangles. Same corresponding angles. Therefore, to prove similarity, we need to prove corresponding angles are equal. There are technically two ways, but we are only focusing on the one this year. So we're going to prove that all corresponding angles are equal. So there's this very specific format that you have to follow. Just like in geometry, we had our equation and our reason. With similarity, we have a very similar setup. So the format is very important. So proving triangles are similar, the format. Since we will always be comparing two triangles, I need to know which triangles I am working with. And since triangles have 3 sides, a triangle name has 3 letters. So we always start by introducing which triangles we are dealing with. So for instance, if we're dealing with triangle ABC and DEF, then we would say in triangle ABC and triangle DEF. It's like English, where you have to have an intro. This is your intro to proving similarity. Now, since we have a triangle that has 3 sides or 3 angles, we need to prove 3 things. So there will be 3 statements, and each statement has to be supported by a reason. So this is just the general format. We will obviously practice with examples. If we can show 3 things, for instance, we are dealing with angles, so a statement about angle 1, a statement about angle 2, and a statement about angle 3. We have proven 3 things, therefore we would finalize and write a conclusion. Triangle ABC, or whatever the triangle is similar to triangle 1, 2, 3, DEF for instance, and the reason would be angle, angle, angle. So that is a format, this portion here, of every single similarity question you will answer in future. You don't have the format, you simply do not get the marks. So let's practice naming those triangles. Yes.
On Wednesday, we saw 1.
Just after 1, yeah, 5 plus 1, I think. Anyone so busy? Okay. So it seems a little silly, okay, saying naming triangles, Ethan, on the board. Now, does it actually matter which letter we put first? Not really, okay? Not when I have a single triangle and I'm only dealing with one single triangle. So this one we can call ABC, we can call ACB, we can call CBA, we can call CAB. Does not really matter. What we do tend to do is put it in alphabetical order. It's all on Lazo. Okay, but any order is fine when it is only one triangle that we are dealing with. Lazlo, your question.
Can't you put something in the middle, something to the B, in the middle? I don't know.
Oh no, because that's not an angle. So an angle, so for instance, A, B, C is an angle in the triangle of A, B, C, specifically that angle at B. This is just, A, B, C is just referring to the triangle as a whole. So then what do I call my second triangle? This one here. Literally anything, because I'm dealing with that one triangle. So any combination of those three letters would be an acceptable name because I'm dealing with it in isolation. I'm just looking at that one triangle and I'm giving it a name using those three letters. But the convention is to do it alphabetically. So I will go P, Q, R. But any other combination would have been fine because I was dealing with one single triangle. But when I work with two triangles at the same time, I need to keep track of which sides are corresponding. So let's make a note. But when dealing with two or more triangles at the same time, the sides must match, they must correspond. So just like we matched sides earlier, we still need to match sides. So if we are matching sides, that means we must match the names as well. Okay, so just draw those two triangles for me, exactly as you see them with the lines and everything. So if I deal only with that first one, what would the conventional triangle name be? ABC, perfect. And that's exactly what we do. The first triangle we name conventionally. But now my second triangle must match my first one. So which side matches, or which letter matches A? Well, we're going to have to look. Okay? Why do we say E?
Because if we rotate it, you can see the
reflect and rotate.
Wonderful. So they are comparing the sides and they are finding where it matches. Okay? So they're using these really cool math terms about reflecting and rotating. Your brain does these things without knowing what they are called. So I'm looking for this line AB, okay, to match to ED or DE, right? Then I know that they're on that same line, but A does not have the right angle, therefore it cannot be D. It must be E. There's my first letter of my second triangle. Now B is my second one. Which matches B in the second triangle? D. And just to check, AC is my long diagonal, my hypotenuse. EF is my hypotenuse. I already found E, therefore C corresponds to. Can you see that that is not alphabetical order, but it is corresponding? They match 100%. So what did we do? We named the first one and then we matched the second one. So let's write that down. And then the bar will probably read. Okay, so when we name those triangles, name the first one, whatever you want, using the 3 letters. And you match the second triangle. What do we match on? We match on those angles. Match based on angles corresponding to each other. So we need that when we compare, because similarity is comparing 2 triangles. And we are comparing the corresponding angles and sides in each triangle. So we need to know what that looks like when it comes to the names. Yes, I think you should. As soon as you've written that down, you can pack your books away. And tomorrow, we're going to put this into practice.